Hello. So in the last class, we had discussed about Noma, where we discussed the basic principle of Noma, and also we discussed about the comparison between Noma and OMA. So just to recap the earlier discussion, in Noma, the R1 achievable rate by user 1 is given by log 1 plus P1 H1 mod square divided by P2. This is H2 mod square plus N naught, and this being the interference term. The interference is coming from the other user, and then you do the SIC, which is successive interference cancellation, and you remove the, the the P1 part, and then you are left with only P2 part, and the R2 in this case is given by log 1 plus P2 mod of H2 square divided by N naught. So there is no interference term here, which you have already deducted, subtracted the user 1 power level. And as far as OMA is concerned, it is given by R1 alpha log 1 plus P1 H mod H1 square divided by alpha N naught, where here alpha is the power coefficient and the resource block allocated in the OMA scheme. And similarly, for the other user, it will be 1 minus alpha, and the resource block will be, the power coefficient will be 1 minus alpha. So this is the value for OMA. And we have also seen the sum rate in case of Noma is higher as compared to OMA if you choose the power allocation scheme appropriately. So now we will try to use this Noma in VLC environment. So what is the motivation for using Noma in VLC? So first of all, multiplexing in power domain. For example, inside a user, in the indoor, there are only limited number of users. We can have multiplexing of user signals. They will have different power gains, and we can multiplex them. So this is the requirement for a power domain Noma. So this is easy in case of visible light communication, for example in an indoor VLC environment. The second thing is that for SIC, you have to estimate the channel. You have to accurately estimate the channel. In RF, there are challenges of as far as estimation of channel is concerned, but VLC is actually a deterministic channel. It does not change with time. It only changes with distance. So user 1 and user 2, depending on the distance, you can always easily estimate the channel in VLC. Noma performs better in high SNR. This we have seen where in the earlier class we had assumed that gamma, which is a SNR tending to infinity, and under those conditions, under this particular condition, we saw that the sum rate for Noma is higher as compared to sum rate of OMA. And in indoor communication, for example, where you're using Noma, you are using the same lamp which is actually there for illumination. So you have enough power at the receiver. So basically you get high SNR at the receiver. So Noma is likely to perform better when you have high SNR. And also you can change the performance or improve the performance of Noma by tuning the irradiance angle and the FOV of the device. For example, this is your LED. It has some irradiance angle. So this is called as half irradiance angle. And you have the receiver here, and the receiver may have some FOV. This is RX, and it will have some FOV. So in order to have high SNR, if LED and the receiver, they're aligned, they can be aligned. If the LED, for example, has a narrow irradiance angle and receiver also has a narrow FOV, so there is almost a direct line of sight communication, and you have high amount of power falling out of the receiver, which is basically a high SNR condition. And we have seen that in high SNR condition, the performance NOMA is much better. So you can actually tune the irradiance angle, this angle, irradiance angle, angle of the device, of the transmitter, and the FOV of the device, in order to get a better performance in NOMA. Or you can optimize the performance by tuning these angles. So now let us understand the block diagram of NOMA in VLC. So suppose you have user X1 here, and then you have user, say, XK, and then you may have user, the last user, say, XN. So these signals, they are superposed in power domain. This is superposition. In power domain, and this superposed signal is transmitted, is given to LED, and this LED transmits and it goes through the optical wireless channel here. So this is optical wireless channel, and of course some noise will get added here, and then there will be noise because of the detector also. Then on the receiver side you have detectors, so there are many the XN detectors, and you first detect the highest power level signal. So if I assume here the power levels assigned to this X1, X2, so this is your T, this is the power level, this is power level assigned to, say, X1, this is, say, to XK, and this is to XN. So these are the power levels defined. This is X1. So there are different power levels given to different user data. And in the first SIC, you detect the highest power level, and once you have detected, for example, in this case, you have detected XN here, then you subtract XN from the remaining superposed signals, and then detect, XN minus 1, and so on till you get X1. So this is basically, you do the SIC operation here, successive interference cancellation. So this is the block diagram of NOMA in VLC. And we also saw why NOMA is preferred in VLC. Now let us try to understand the VLC channel model, which actually we had done when we were discussing indoor channel modeling. So in this model, this is the LED, this is a transmitter here, and then you have the receiver here, and this is the half irradiance angle of the transmitter, and psi I is the angle which the normal of the transmitter makes with the line of sight. So this is the emergence angle, one can call it, emergence. And similarly, phi C is the FOV. Any light falling out of this phi C will not be captured by the receiver. and phi I is the angle which the normal of the receiver makes with the line of sight. And the distance between the transmitter and receiver is shown here as di. Now, the channel coefficient for such a VLC channel is given by Hi AI, which is the power of the receiver, divided by di square, that is distance square, that is the source, distance from the source to the user, and R0 psi. So I'll just discuss about this R0 psi in a bit, in a little after some time. So this is psi I, and then you have a filter gain, which is function of, so this will be phi I, function of this, and then you have the concentrator gain, which is represented as G, and this will be phi I, and you have cos phi I. So this is valid when the phi I angle is between phi C and 0. Otherwise, this value is 0 otherwise. Or when phi I is greater than the phi C, which is the FOV. So it is given by AI divided by distance square into R0 psi I into TS phi I. This is the filter gain, which is used as a receiver. This is the concentrator gain, which is again used as a receiver. And G psi, that is the concentrator gain, G phi I rather, is given by refractive index of the concentrator divided by sine square phi C. So this is the refractive index of the concentrator. Now let us see what is this R0 psi, and this we had discussed also earlier. R0 psi I is pattern of the LED. And it is given by m plus 1 over 2 pi cos m psi I, where m is the Lambertian parameter. So it basically tells about the beam, whether it is a narrow beam or a wide beam, depending on the value of m. So this is pattern of the radiation pattern of the device. And this can be this m, which is defined as minus log natural 2 divided by log natural cos, that is irradiance angle, which is half irradiance angle of the transmitter. In addition to this, the receiver will have noise, which is a short noise and thermal noise. So the total noise will be sigma square is equal to sigma square short plus sigma square thermal. So this is a VLC channel model which we will use in our analysis. Now let us try to understand for a case where there are two LEDs, LED 1 and LED 2, and there are three users. One user is in the atto cell of LED 1, this is the user 1. The second user is in the atto cell of LED 2, so this is user 2. And user 3 actually gets intensity or light both from LED 1 and LED 2. So this user is actually on the edge of the Atto cell for each LED. So this gets light from, this is user 3, this gets light, U3 gets light from both the LEDs. And in the same way, we have defined different angles. So for example, this is Shy 11, which is the normal makes with the line of sight. And then you have 511, the normal makes of the receiver makes with the line of sight. D11 is the distance within LED 1 and user 1. And similarly, you have for user 2 here, this Shy 22, Phi 22, and the distance is D22. And this user 3 actually gets light from both from LED 1 and LED 2. And these are the angles which are defined. And the distances are actually D13 from LED 1 to user 3 and D23 from LED 2 to user 3. So this is the system model which we want to evaluate. So now, having understood this system model, let us try to analyze this Noma in VLC. So ZL is equal to PLJ XJ, where J belongs to GL. So this ZL is actually signal transmitted from LED L. And this GL is set of users connected to Lth LED. So in our case, we have LED 1 and LED 2. And the users which are connected to LED 1 are U1 and U3. And users which are connected to LED 2 are U2 and U3. So this GL is the set of users connected to the Lth LED. And J is the user. So this is the user. And PLJ is the power. The PL is the total power. And this is the power from the LED to the Jth user, PLJ. And the total power from the LED is PL, which is summation of all the users which are connected to Lth LED. So if where capital L is the number of LEDs. So if you see the power at Yi, received signal Y, it will be summation from L is equal to 1 to L, where L is the number of LEDs, summation J belonging to GL, HLI coefficient into PLJ into XJ is the data plus the noise. That is the received signal of the ith user. The HLI, the channel coefficient between Lth LED and the ith user is given by this. AI is the area of the receiver. This is the distance, d square Li, m plus 1 divided by 2 pi, where m is the Lambertian parameter, So this is Chi Li, and then you have the filter gain. This I have used the indoor channel model as I had discussed earlier. This is the concentrator gain and the cos Chi Li, and this is only valid when the phi Li is between 0 and FOV. This is FOV. And for phi Li greater than phi C, it is 0. So having modeled HLI, now we see that this HLI is actually, among other parameters, it is proportional to 1 by distance raised to the power m plus 2 and sine square phi I. So this is actually coming from that concentrator gain. And if you see here, this cos psi, if you see here, for example, cos psi I is the distance, the height of the between the transmitter and the receiver divided by distance. So cos m psi I will be some proportional to 1 by dm, and the other, the square term is coming from here. So this becomes actually d raised to power m plus 2. So m is becoming because of the Lambertian pattern of the LED and then square term. So this whole thing becomes 1 by d m by 2. And the same thing I have written here. So this is distance raised to power m plus 2 into concentrator gain. And the SNR, gamma I, that is the instantaneous SNR, gamma I is sum of I is equal to 1 to L HLIPI, and this is the interference term. This is plus sigma I square, and this is for k is equal to I. We will understand why this k is k greater than I. So this is the instantaneous SNR. Now we are doing the decoding in the following fashion. So the decoding is performed in the order of increasing channel gain. In the order of increasing channel gain. This is what we had studied in Noma. The decoding is performed in the order of increasing channel gain. The interference from users of higher decoding order UK with k greater than I is treated as noise. So this is what, if you see in the instantaneous SNR expression, SINR rather, treated as noise. So anything greater than k plus I is treated as noise because at every stage we are subtracting the detected signal and rest of the signals are actually noise. And when we subtract the detected signal, then the remaining signal, again one uses successive information cancellation, successive interference cancellation scheme and detect the next higher power level, and then so on and so forth the process goes. So the interference from users of higher decoding order with k greater than I is treated as noise. So we follow here a pattern for decoding. So this is for the users which are inside the Atto cell. So this DLC, L is the LED. So these are the users which are actually directly below the LED, or they are only covered by LF LED. There is no light coming from any other LED. So depending on the distance, these users are decoded in this fashion. So this is, these are the core users which are covered by the LED, and these are the edge users which are there on the edge of the Atto cell, and they may be getting light from other sources. So this is edge users. So first only core users are decoded, and then subsequently the edge users are decoded. So edge users, let me write here, edge users are moved to end of the decoding order. edge users decode their signals after subtracting the signals intended for other users in both the cells. So this becomes the decoding order final. You have the core users here and then the edge users here. So this is the decoding order which is followed here. So now let us discuss about the power allocation scheme, how power is allocated to different signals. So assume that there is a central controller which has the information of the position of the users, what is the distance from the transmitter, and also channel conditions. So the central controller, has information, and accordingly it gives power to different users. So it knows the distance of the user, for example, distance, it knows the channel condition. Of course, position is also known, only then you can find out the distance. So all these things are known by the central controller. Based on these inputs, the power is allocated to different users. So there can be two possibilities. One is, static power allocation. Other is gain ratio power allocation, or also called as GRPA. So in static power allocation, you have, for example, PI is given as Pi minus 1. So alpha is the coefficient. So suppose power to P1 will be alpha P0. If P0 is the power to the user number 0, then the user 1 will get alpha P0. So this is one way of allocating this is a static way of allocating power. The other one is a gain ratio power allocation, or GRPA. So this basically depends on the power given to the ith user, power allocated to the ith user is given by H1 divided by Hi raised to power I Pi minus 1. So H1 is the first sorted user. So this is with respect to the first sorted user. First sorted user. So suppose there are 3 users, then P1 will be H1 over H1 raised to power 1, P0, P2 will be H1 over H2 raised to power 2, P1, and P3 will be H1 over H3 raised to power 3, P2. So this is how the power will be allocated. And then this I, which you see here, is actually for fairness. The signals which are being detected first, they have noise coming from rest of the users. So they have to be given more power. And this is how the power distribution is done, and which actually ensures that there is a fairness among different user signals. So this raised to power I is the fairness, and we assume that H1 greater than H2 greater than H3, depending upon where those users are located. So the power allocation will be P1 less than P2 less than P3. So this is how the power is allocated in GRPA, gain ratio power allocation. And if you see the results for both static and GRPA, this is assuming fixed allocation, static allocation, where alpha is kept as 0.3, and for alpha is equal to 0.4, there is little improvement here. And but if you use GRPA, then the gain is much more as compared to static allocation. So this is for GRPA. So suppose I want to see -6, I can support 5 number of users with this quality of service having BER of 10⁻⁻6. Whereas if I do the static allocation, probably I cannot achieve -6, and only less number of users can be supported in case of static power allocation if I keep my criteria of bit error rate as 10⁻⁻6. So there are other techniques also, power allocation technique, which can give further improvement. So this is just to show a difference between a static power allocation scheme and a little modified power allocation scheme. And we have seen that modified power allocation schemes gives a better performance as compared to static. So there are few issues with Noma, which are being people are working on to solve some of these issues. One of the main issue is hardware complexity, because you are doing successive information at each stage, and this actually consumes power also. And if user has for example, a mobile, it has limited battery, so the power may be consumed for decoding Noma. So this is one issue. The other issue is successive interference cancellation requires a lot of hardware processes. So it is hardware complex, and also there may be a latency issues because the last user is detected last after subtracting all previous users who have higher power levels. So this might introduce some sort of latency. So these are some of the issues which have to be addressed in Noma, and they are being addressed as well. The other issue is that error propagation and SIC implementation. So actually the whole process of SIC depends on how accurate is your channel estimation. So if channel estimation is not accurate, you may detect or decode the signal wrongly, and then when you subtract, this way when you subtract, it might affect decoding of subsequent signals. So the error may propagate if you are using SIC and your estimation of higher power signals is not accurate. So this is another issue which has to be addressed. So for example, to address, for example, hardware complexity, sometimes you make clusters of users so that there are only less number of users in that area, and then SIC process is little easier as compared to if there are more number of users. And the third issue is optimal pilot allocation, that is perfect or near perfect CSI is required. So how many pilot symbols you require, because adding pilot is basically adding to the overhead. So there has to be some optimum size of pilot allocation so that you have near perfect channel state information, which is actually the core principle of SIC, the estimation of the channel. So this is another area where a lot of work is being done. And the second and the last thing is the carrier frequency offset. In OFDM, we had studied that this CFO actually carrier frequency offset degrades the performance of the system. Basically, it will spoil the orthogonality in OFDM. And this happens because the local oscillator frequency may be changing. And it also introducing timing offset. So basically with this timing offset, there will be jitter. So in RF, this estimation of CFO, carrier frequency offset, and timing offset, there are a lot of techniques available and it can be done easily. But whereas in case of NOMA, CFO and timing offset becomes little challenging because NOMA has overlapped signals. In OFDM, you can always distinguish between the signals because they are orthogonal. So it becomes little easier, estimating and correcting CFO and timing offset. And it's little tedious when it comes to NOMA. So these are some of the issues with NOMA which are being addressed by research community. So the challenges in power domain NOMA, this is power domain. Whatever we have studied is actually power domain only because we are sending signals at different power levels. So power allocation strategy. Now we studied a simple example of static and a GRPA, that is a modified, which depends on the gain ratio, power allocation. So we saw improvement in GRPA. So there can be other technique also. There can be still another better technique which can give you, better advantage as compared to this existing scheme. So power allocation strategy is one has to look for an efficient power allocation strategy which gives the best performance in NOMA. The second challenge is actually clipping effect. This effect may not be there in baseband transmission, but in OFDM, as we know, in OFDM the signals are complex and bipolar. And to the LED, I cannot give this complex and bipolar signals. To LED, the signals have to be real and unipolar. So there has to be some conversion process which will make the complex bipolar signal into real unipolar signal. So we did this when we were discussing OFDM, and we discussed two schemes, DCO OFDM, where you give a DC shift to the signal, and the other was ACO OFDM. In DCO OFDM, actually you give a DC shift, so there's a constant DC current flows, so it makes this signal as power inefficient, and the spikes in the signals are large. I mean, you cannot make everything positive. So normally you give some minimum amount of DC shift and you clip rest of the part. So basically you introduce some sort of clipping distortion. So with this and ACO also, you clip the signal, the lower half is clipped. So there is a clipping distortion happening both in DCO FDM and ACO FDM. And this may degrade the performance of NOVA because of this clipping. The third is security. Now we are actually sending the superposed signals where signals from all the users are getting combined. So it is a security threat. So what normally is done that you have the security at higher levels. You do the encryption at higher levels, whereas you transmit the data over the physical layer. But then when you are sending high amount of data, then having security at higher level will introduce some sort of delay. So you want to have security in the physical layer itself. So some PLS or physical layer security is to be ensured when you are dealing with power domain NOMA. There are issues of intracellular interference and interchannel interference. So this also have to be studied. And the last challenge is non-linearity of the LED. So if you see the characteristic of LED, this is a voltage or current, this is power. So this is not linear actually here, and then it saturates. So this is not fully linear, so this is non-linear, and it saturates after a certain. So basically it will limit the dynamic range, because after that it starts saturating. So you can have only power levels which are dictated by the dynamic range of the LED. So this is one limitation here. And this non-linearity may also, because of different constellations, will suffer due to this non-linearity, and this will degrade the overall performance. So while doing this, one has to take care of this non-linearity, and there are different models available. Volterra is one example which takes care of the non-linearity of the device and hence improves the performance. So one has to handle this non-linearity, and also one has to keep in mind the dynamic range of the device. So, and these two limitations actually there are some challenges posed in power domain Noma Vlc because of these two limitations. So these are some of the issues which are being currently addressed by the research community. So this was regarding use of Noma in VLC. So we have studied about Noma initially, and we also now seen in this lecture how Noma can be used in VLC environment. The next we will study how Noma and MIMO can be used in VLC environment, because in RF, if you see, the Noma and MIMO, they generally go together. That is in RF. So before we go to Noma, MIMO in VLC environment, in the next lecture I will give some basics of MIMO, and then we will move to how to use Noma, MIMO in VLC environment. So that will complete the discussion of use of Noma in visible light communication. Thank you.